facilitating safe sim-to-real through simulator abstraction and zero-shot task composition. In order to deploy autonomous robots in the solving of complex real-world tasks, these robots need to be trained in some way. Training a robot in the real world can be incredibly difficult, however, due to potentially very long training times, high operating costs, and the danger a robot may pose to itself and the environment around it. Ideally, we should be able to train an agent in simulation, where these limiting factors do not apply, and then transfer the knowledge gained to a real robot operating in a real environment. Consider, for example, this 4-room grid world domain, where the robot must navigate a set of rooms. The starting room, the target room, and the state of the doors between rooms may vary. Learning to perform all possible tasks in this environment by learning a policy for each task individually is infeasible even in simulation. Thus, we employ value function composition. Basic tasks, for example, navigating to the top rooms or to the left rooms, can be learned by the simulated agent, and operations can be performed on the value functions learned to derive value functions for more complex tasks composed of these basic tasks, such as going to the top room and not the left room, or going to the room that is not the top and not the left, with the south door closed. In order to avoid the difficulties in creating a high-fidelity simulation of the target environment and training in that high-fidelity simulation, we employ a simple, low-fidelity simulation composed of discrete low-level actions that approximates the target environment. In our example, these actions are moving forward, turning left or right, and ending the episode. Training the robot to perform these low-level actions in isolation is relatively easy and safe, compared to learning to perform the full task. This merely requires a mapping from states in the simulated environment to some representation of the real-world environment. In our experiments, this is achieved by suspending a webcam over the environment and using color detection to locate the robot. Once we have learned the basic tasks in simulation, and the low-level actions that compose these tasks on the robot, we can perform direct transfer, with the learned policy in simulation outputting the steps the robot needs to take to complete the task. Execution time on the robot is fast, but success rate and final distance to the goal are less than ideal, due to noise introduced by real-world factors, such as the robot's particular construction and friction with the floor, as well as the discretization of the real world. To overcome these difficulties while still gaining the benefits of using a low-fidelity simulator, we employ simple error correction. At any point, the robot can assess its own location, as well as the location it should be at according to the simulation. If the robot has deviated, it can perform a simple path planning approach to correct this deviation. In this experiment, we perform error correction after executing every low-level action. As a result, the robot completes the task in a safe and accurate manner, avoiding all obstacles and reaching the target coordinate. However, the time taken to complete the task grows significantly due to the large number of correction steps. To speed up execution on the robot and reduce the number of error-correcting steps while remaining safe and still benefiting from the combinatorial learning power of compositional RL in a low-fidelity simulation, we instead learn complex tasks as a sequence of temporally ordered tasks. In our example, these tasks consist of moving to a doorway or to the center of a room. These tasks create natural points after which error correction can be performed. Thus, the robot can correct at key points in a trajectory rather than after every single low-level action. In our experiments, this temporal logic approach with task-level error correction executes more quickly and with fewer corrections than before, while still maintaining high success rate and accuracy in position. To further compare these approaches, we perform experiments in a more complex task in the same environment. Solving the task requires a long trajectory, over which many errors can accumulate when transferring from simulation to the real world. Indeed, with direct transfer and no error correction, the robot is unable to complete a single run due to the complexity of the task. As before, value function composition with error correction after every low-level action performs relatively safely and accurately, at the cost of execution time, due to the large number of corrections being performed. Employing temporal logics, we can exploit the hierarchical nature of the problem to greatly reduce the number of error correction steps needed, performing the task safely, accurately, and in good time despite the longer trajectory. In conclusion, our framework, which consists of training an agent in a low-fidelity simulation with temporal logic composition, and then transferring the learned policies to the real world, error correcting to the expected state after every task execution, provides a simple, low-complexity solution to solving a combinatorial explosion of tasks in simulation and transferring the learned skills to the real world in a safe and accurate fashion.